considerations. So if we go back into the mid to late 1800s, there were a few refrigerants being used in refrigeration systems, one of them being carbonic acid. That was listed as that's basically an A1 refrigerant by today's standards. 1873, so we got ammonia, methyl ether, sulfur dioxide, methyl chloride. So what these refrigerants all had in common, or most of them anyways, was some properties that were, let's say, a little less than safe. So we're dealing with the first one there, carbonic acid, is high pressure. And then you've got other ones, the B2, for example, B1s, B2, B1s. Those would be classified as a toxic refrigerant. And then the A3, of course, being a very flammable refrigerant. And even with the B2s, of course, the 2 indicates that they're moderately flammable. So we're dealing with refrigerants that are flammable and or toxic. Okay, and in the first case, carbonic acid, we're dealing with a refrigerant that is high pressure. Now, carbonic acid, for those of you who don't know, is actually CO2 with moisture in it. That's basically what it is. You could consider it wet CO2. So by today's standards, we couldn't use carbonic acid in refrigeration systems, as we need a CO2 that's quite dry. CO2 is in the A1 safety group. Non-toxic, non-flammable, has an ozone depletion potential of 0, of course. That's because it does not contain any chlorine. Its global warming potential is very low at 1 and is not subject to any phase-out regulations. But keep in mind, when we do talk about CO2, even though I'll refer to it as CO2, as most of us commonly do in the business, CO2 officially as a refrigerant is known as R744, and only R744 should be used in systems, carbon dioxide type systems. So taking a brief look at some history here, some more history. Alexander Twining was a gentleman that proposed the use of carbonic acid in his 1850 British patent. So CO2 was used many years ago, of course, in its subcritical state. Thaddeus Lowe and others developed early refrigerating equipment also that utilize CO2. And you see a picture of the Titanic, and you might be wondering why I just dropped that on the page. Well, this is something I learned from Garth Dennison, a friend of mine years ago, is that actually the Titanic, interestingly, had a CO2 system on there. It had 2 horizontal duplex refrigerating engines, as they call them, on there. So that was pretty interesting. And that was used for cooling the glycol that was pumped throughout the ship. Widespread availability and safety characteristics made CO2 a very attractive refrigerant. In fact, it became the choice for transporting frozen foods around the world during the 1890s. And by 1910, there were approximately 1,800 CO2 refrigerated ships in service, believe it or not. So transporting things like meat products from continent to continent, CO2 is a big part of it back in the day. CO2 in marine applications peaked in the 1930s. And then, as you know, in the 1930s came along the synthetic refrigerants. So some of the earlier ones, such as the R12 and 500, and I guess at some point 502, and later on around World War II was R22. These are all synthetic refrigerants. And then over time, we learned that there were issues with these refrigerants, right? So we had the ozone depletion, and now more of a attention is being placed on the global warming potential side of it. So long and short of this is that natural refrigerants, we're seeing renewed interest in this, have been for many years around the world. So refrigerants such as ammonia, CO2, of course, and hydrocarbons, propane, for example, are in some cases making a comeback, and in other cases they're just continuing along as they always have been as players in the business. More recently, though, many technologies have been introduced in order to be able to harness these the benefits of CO2, which we'll talk about. And some of them I mentioned before, the high pressure challenge. So many of you may be familiar with transcritical refrigeration. We'll talk about that another day, as you know. Transcritical compressors is one of these innovations. Flash gas bypass, not really a new innovation, but something that's been used for many years. And as it turns out, it works out to be a really good technology for CO2 booster type systems. And other controls and such to address the absence in a relationship between pressure and temperature. Okay, so what I mean by that is you can't look up when the refrigerant's above the critical point, you can't take your temperature pressure chart, look up a pressure and find out what saturation temperature is, because there's absolutely no relationship between pressure and temperature when we get above the critical point. So in this case, the high pressure valve, some people call them the magic valve. I've called them the algorithm driven regulators, because instead of having a regulator that just has a pressure set point or some kind of temperature set point, or maybe something like that, it actually has to calculate the position on the fly, depending on a couple of a few inputs that it receives from system sensors. And we'll talk about this when we get into the transcritical side of things. The other thing too is improving the efficiency of transcritical. So transcritical CO2 refrigeration, in the early days, engineers they were very critical of CO2 because the efficiencies didn't appear to be as good as what they were used to in other systems. But over time, there's been many patents that have been filed, many technologies produced to improve the efficiency of CO2. And some of these technologies are actually not new, but they, for example, heat reclaim and things like that, even ejectors for that matter. But applying these other technologies, some new technologies, some existing technologies, enables us to improve the efficiency of CO2 systems when they are running transcritically. Generally, when you're running subcritically, it's quite efficient anyways. Now, Gustav Lorentzen is a gentleman that he was with the Norwegian University of Science and Technology. He was credited for the rediscovery of CO2. And here's a gentleman, I guess, that thought, why are we always so focused on subcritical refrigeration? Why do we have to always work below the critical point? Why don't we drive that or transcend this critical point and operate transcritically as a supercritical fluid? And this is exactly what he proposed. And then he even developed a transcritical cycle in the late 1980s to early 1990s. So here's a look at the CO2 phase diagram. All refrigerants have a phase diagram, like they have pressure temperature charts and pressure enthalpy diagrams and what have you. Just taking a quick look at this, you can see that there's an area where we have a solid, liquid, vapor, which we're most familiar with in refrigeration systems. And then you have this area up here, supercritical fluid, which we're going to talk more about. So if we take a look at 1 atmosphere, dry ice, for example, a solid, CO2 is dry ice, it will actually sublime directly from a solid to a vapor at 1 atmosphere. The triple point for CO2 is approximately minus 70 Fahrenheit, which corresponds to approximately 75 PSI. And then the critical point is actually quite low at 87 degrees, 87.8 degrees Fahrenheit. And note that the pressure at the critical point is 1070 PSI. So this slide compares CO2 to some other refrigerants, 404, ammonia, 134A. I just picked 3 other refrigerants to compare this with, and I pulled these properties out of RefProp. And this is actually similar to a slide that I saw in in some Danfoss literature a few years ago, and I like how it actually points out, it graphically shows the difference between CO2 and other refrigerants. So here again, we have the critical point of CO2 being just under 88 degrees Fahrenheit, and the triple point is actually quite high compared to other refrigerants at approximately minus 70 degrees Fahrenheit. And again, that's approximately 75 PSI. So the actual working range, okay, so between triple point and critical point is where we're working with liquid and vapor. And whether a system runs subcritically or transcritically, what we're seeing in the evaporator side is business as usual. We take a pound of liquid and you boil it off. All that latent heat is absorbed from the surroundings. Okay, so that'd be the other side of the evaporator to cool air or some fluid or what have you. But the overall working range is quite a bit lower than these other refrigerants. So there's one point right there is on the evaporator side. No matter what, we're always dealing with liquid and then eventually vapor. So now let's talk about the physical states of the CO2. Initially here, we're looking at CO2 in its solid state, which, as I mentioned, is dry ice, which sublimes directly to a vapor at a pressure of 14.7 psia. So, and that corresponds to a temperature, by the way, of minus 109 Fahrenheit. I didn't mention that on the previous slide, but very, very cold. Here we can see this looks like just a typical sight glass, and you can see liquid in the bottom of the sight glass, vapor in the top, and then we can see this clear meniscus, which is basically your separation line in this two-phase glass here. So if we were to take this sample of CO2 and heat it up towards its critical point, we would notice that the density, but what we notice is that the meniscus would begin to disappear, and eventually will disappear 100% when we have supercritical fluid. There is no difference. There is no liquid. There's no vapor. It's now a supercritical fluid. But you'll notice that with any refrigerant, when you look at a pressure enthalpy diagram, the saturated liquid curve and the saturated vapor curve, as you increase the pressure, okay, they end up the point where the densities become the same. Okay, so that's a characteristic of all refrigerants, but it's something we think about with CO2 because CO2 is really the only refrigerant, to my knowledge, that we work with transcritically around the world. So again, the critical point here is 88 degrees Fahrenheit, or just under that. Again, above this point, we're talking about a supercritical fluid, not to be confused with transcritical. Transcritical just means that during the compression process, we transcended the critical point, so we call it transcritical. And when we get into that, we transcend the critical point, then we're working with a supercritical fluid. So on the discharge of a transcritical compressor, that would be supercritical fluid, and that's what enters the gas cooler is supercritical fluid. Again, a talk for transcritical refrigeration. Again, we cannot distinguish between a liquid and vapor, and we cannot use pressure to determine the temperature on the high side of the system when it's in a transcritical, when we're operating transcritically. So when the refrigerant's supercritical, there's no relationship between pressure and temperature at all. And when we remove heat from the supercritical fluid, note that it's a sensible heat rejection process. Okay, and the reason for this is, for a given pressure, your temperature is dropping with the CO2. And this is why they're called gas coolers instead of condensers, by the way. A gas cooler is actually just taking the heat out of the refrigerant and reducing its temperature. So as the CO2 transcends the critical point, as I mentioned, no distinction between liquid and vapor can be made, and the meniscus completely vanishes and a supercritical fluid appears. So if you want to know what it looks like, there it is right there. I know not a lot to see there, but Note that unlike other refrigerants we're familiar with, that where we're working subcritically, you can't condense liquid. You cannot reform any liquid by increasing the pressure in this case. Okay, once you're above the critical point, we can no longer make liquid by increasing pressure. A very, very interesting set of characteristics about CO2. As a supercritical fluid, it has the high density of a liquid and has the high diffusivity of a vapor. So it works to fill or occupy the internal volume of a container or a system as a vapor would, but it has the high density of a liquid at the same time. And just a couple of points of interest. Supercritical CO2 is actually used during the decaffeination process of tea leaves and green coffee beans. It's also used in supercritical fluid extraction processes. So we know that CO2 has a low critical temperature at approximately 88 degrees Fahrenheit. It has a high vapor density. It has a high vapor pressure. In fact, system pressures in CO2 plants are, we could say 5 to 6 times or so, and up to 2000 PSI. Now that's generally quite a bit higher than where we would normally run them at, but the compressors and such are rated generally up to these higher pressures. So it's quite high compared to that of HFCs and even ammonia. So again, when we get into these very high heat sink temperatures, well, specifically above that critical point, heat can only be rejected in the supercritical state. And this is where the learning has really taken place with CO2 is, for the most part, aside from safety aspects of it, it's what's going on in the high side of that system. If we take a high level look at some density and pressure comparisons of CO2 compared to other refrigerants, we can see that, as the temperature increases, we can see a rather rapid increase in pressure, but also density for CO2 also. Just an interesting sidebar, CO2, generally your difference in pipe diameters between liquid lines and suction lines is quite a bit lower than what we would see with traditional HFC systems. So, instead of having like a 1 1/8 suction line and maybe it's a half-inch liquid line or something, it might only be a 5/8 or a 7/8 suction line and a 3/8 liquid. So the pipes are smaller because of the higher densities, but they're also closer together in terms of their diameter between liquid and suction line. CO2 has a high thermal conductivity, making it good in heat exchangers. We get good heat exchange in heat exchangers, and therefore leads to higher heat transfer coefficients in those heat exchangers. And with these high heat transfer coefficients and the higher thermal conductivity, we can generally operate CO2 evaporators, say, at just a few degrees higher than perhaps you could with R404 or 507, and that's assuming the same air side fin temperature. We can generally operate at lower temperature differences, a slightly lower temperature difference anyways, between CO2 and the cooling medium in gas coolers, cascade heat exchangers, liquid to suction heat exchangers, anything that's a heat exchanger basically. So just to compare thermal conductivities, well, we can see that CO2, although it may not have much on ammonia, it does quite well compared to other HFC refrigerants that we've been familiar with for the last several years. CO2 also has a low viscosity, and in fact, it has a viscosity that's approximately 1/10 of water, that of water at 40 degrees Fahrenheit. And unlike glycols, the viscosity is fairly constant at low temperatures. So as the low temperature varies, the viscosity doesn't change as much as it would with other types of glycols and heat transfer fluids. And due to the low viscosity, the pumping power requirement for CO2 is lower than for glycols. So CO2 is actually used as a heat transfer fluid, not necessarily in pressurized equipment, but also just to be pumped around and extract heat from a heat source. So the low viscosity and the high thermal conductivity actually makes CO2 an attractive heat transfer fluid also. Viscosity, CO2, here again, you can see how it pairs up with other refrigerants, or how it stacks up, I guess I should say. The viscosity is actually considerably lower than other HFC refrigerants and even ammonia. CO2 offers an abundance of pressure, and that may just sound strange, but the next couple of slides, it'll make a little more sense. But basically, think about it this way: suction line pressure drop is going to have less influence on the saturation temperature, so you could actually reduce. We could see more pressure drop in the suction line before we see a drop in saturation temperature. Now, keep in mind this point here: lower suction pressure always reduces both compressor capacity and efficiency. Whether it's a CO2 system or an HFC system or ammonia system or what have you, generally the goal is to design for, you know, the lowest pressure drops that are practical in the system, because we have to think about oil return and everything else. And so it's another one of those cases: just because we can do it doesn't mean we should. We're still working to get the highest efficiency out of systems possible, even with these natural refrigerants. So here's a way of showing this. This graph goes from, as you can see, -40 up to +40. At -40, the pressure drop at -40, we could see that for CO2 would be approximately 3 psi per 1 degree Fahrenheit. For similar refrigerants such as 404, 507, 448, 449, and ammonia, and that it's down around approximately a third of a degree. And if we look at +40, we can see that you would need an 8-pound pressure drop in order to have a 1 degree drop in saturation temperature. Whereas with other HFCs and even ammonia, it's going to be approximately 1.5 psi in order to see a 1 degree drop in saturation temperature. So as always, things are more critical when we get into the lower temperatures, whether it's CO2 or HFCs and what have you. But you can see quite the difference between CO2 and other refrigerants here in terms of its the effect of the pressure drop. Taking a high-level look, now I've got very few refrigerants that I'm showing for comparative purposes here, but you can see with CO2, compared to most of your HFC refrigerants, I think, you know, 65, 70, 75, 80, 85, something like that, BTUs per pound. CO2 would be sitting around 140 BTUs per pound, down at the -40 range, just to give you an idea about the latent heat capability of CO2. So, you know, perhaps nowhere near that of ammonia, but hey, ammonia has its other challenges as well, right? We know that to be a toxic, flammable refrigerant, great refrigerating capacity, but other challenges: high discharge temperatures. Every refrigerant has to be treated differently, and in the case of CO2, with what, you know, the industry has learned about it, we've been able to apply new technologies, new ways of handling the refrigerants, new ways of designing systems to make them the most efficient and safest solutions possible. Note that CO2 also has quite a high solubility. So this is the water solubility in various refrigerants here compared to CO2. Actually, with CO2, it's very low, okay, compared to other refrigerants. In other words, it's less forgiving. Okay, and another way to look at this with CO2 is the maximum solubility of this is the water solubility in CO2. You can see in its liquid phase, it has quite a high solubility, but in the vapor phase, it's somewhat less. So you're going to have a problem with that once the the liquid is expanded and becomes vapor. Then the solubility of the refrigerant becomes less. So I guess the moral of the story here is systems need to be super dry. We need to be very careful to make sure that moisture levels are kept at their absolute minimum, so we don't create any chemical reactions, corrosion, things like that in the system. Just to take a look at some CO2 safety aspects, you can kind of at a high level see what they are here. One of them is relating to pressure, or the rate of pressure increase I was talking about. And I'll give you an example of, what happens to a CO2 cylinder, the pressure inside that cylinder as we increase the temperature around it. Dry ice as another situation. And then this one here, CO2 is an asphyxiant. Okay. And I'll explain that actually a little more on the next slide, but we could broadly classify refrigerants. First of all, we have those that have no particular odor or taste, no short-term toxic effect. For example, the fluorocarbons, hydrocarbons, even nitrogen. Those that have strong odor and acute toxic effect, such as ammonia, sulfur dioxide, methyl chloride. These are the earlier refrigerants that I mentioned that were used many, many years ago in the 1800s, early 1900s. Then we have those that are directly involved in the respiration process, such as carbon dioxide, water, and nitrogen. So CO2 is odorless and colorless. It displaces atmospheric oxygen. This is very important to know. It's a suffocating gas in higher concentrations. Okay, so basically what this means is that CO2 will displace oxygen even in your lungs. Okay, generally the body is taking in oxygen. The oxygen gets transported to the various parts of the body, where it then extracts CO2 from the tissues and what have you, brings it back to the lungs, and then we exhale that CO2. In the presence of CO2, if we have a high concentration of CO2, then the oxygen can't really get in there, because the hemoglobin, the CO2 rather, has a higher affinity to hemoglobin and red blood cells than O2. So this is why concentrations are it's very important that they're kept below certain limits in mechanical rooms and what have you. And because it's odorless and colorless, can make it fairly hard to detect. Oftentimes it may only be the oil that you see as a mist. Some of the influences as a result of not being able to have the body take in oxygen as it needs it and get rid of that CO2. Just looking at the various concentrations, I just got this from Wikipedia here, so you can have a look at that. At the 1% level, drowsiness, 3% mild narcosis, reduced hearing, increased heart rate and blood pressure. At the 5% level would be shortness of breath, headaches, dizziness, confusion. And at 8%, things just progress, dim sight, unconsciousness, sweating, things like that. That's why it's very important that we have mechanical rooms set up so that we have protection against these high levels of CO2. And that's why the codes and standards exist. Basically, the leak detection equipment in mechanical rooms would be calibrated to no higher than 5,000 parts per million, which is your occupational exposure limit per the ASHRAE 34. Okay, and that corresponds to, this is a threshold limit value based on an 8-hour time-weighted average. So gas sensors or oxygen deprivation sensors should be used in accordance with the code, always, in accordance with the code. And a safety code for mechanical refrigeration would generally be there's CSA B52 for here in Canada. And we should also consider what's in the contents of the B34, ASHRAE B34, and ASHRAE 15, which is the safety standard. Generally, the CO2 sensors are installed at a low level, close to the ground, say approximately 12 inches or so, and due to the higher density than air. So the density is approximately 150% greater. Of course, as with any system, we need to have protection against excessive pressure. So cylinders are designed to be safe with relief devices. They're built to be strong enough to contain the pressure, the high pressure. In addition to this, systems also need to be designed for any potential high pressures that could take place. And what we'll talk about here is just an example of using a cylinder. What happens when you increase the temperature of a refrigerant in a cylinder up to a certain point? It's trapped, it's contained within that same volume. So it can't really grow, it can't expand anywhere. So the pressure has to increase. And we'll see what that rate of pressure increase is going to be like. So to simulate the example, you would have CO2 trapped in a cylinder, something you'd never ever want to do. This is just what I'm explaining for informational purposes, but this is the case with HFCs, and this is the case with HFOs and ammonia and any refrigerant that we use. You never ever want to trap liquid in a section of a system. It will get quite dangerous. It results in a hydrostatic condition, any heat added to that, and it's going to rupture. So we have to be very, very careful of this, very aware of it. The increase in temperature around a cylinder, of course, is going to determine the corresponding increase in temperature. Okay, so the volume again is fixed. So as we increase the temperature, the pressure, of course, is going to increase. Now, if the pressure exceeds the maximum pressure capability of the vessel, I think we know what can happen next. The situation can get quite dangerous, and this has happened with propane tanks, not even in the refrigeration, air conditioning sector, but any cylinder used in any industry that can exceed its maximum pressures, and especially if it's charged completely filled with liquid, which our refrigerant cylinders are not. They're generally charged with a fairly high fraction of liquid, but there's always a vapor pocket at the top. So as I mentioned before, the rate of increase, pressure increase rather, for CO2 is quite a bit. It's greater than other refrigerants. So for an example, if we take a look at a 50-liter cylinder, which has an internal volume of approximately, it's 0.05 cubic meters or 1.77 cubic feet, and we fill that in this case 36.6 pounds of two-phase CO2 having a high liquid fraction of 90%, which means 90% liquid, 10% vapor. Okay, and then at an initial temperature of -20. That's pretty cold. Maybe it's sitting in a cold truck or something like that. Our assumed conditions at the end, well, we're going to warm this cylinder up first to an ambient temperature of 80 degrees Fahrenheit. Then we'll further heat this up to 120 degrees Fahrenheit. And we'll just see what happens. What is the resulting pressure? So initially the cylinder sits at 20 psi, -20 Fahrenheit. Okay, again with 90% liquid. It starts out at a pressure of 215 psia and increases to 970. And keep in mind, we're only at 80 degrees Fahrenheit and we're still below the subcritical point. So if we were to further increase, add more heat to that cylinder to a point where we bring it up to 120 degrees Fahrenheit, now we're going to follow this constant volume line, and we end up with a pressure of 1,365 psia, just to give you an idea of what the pressure increase would be when we go through a temperature range of -20 to 120 degrees Fahrenheit. For our 507, the overall increase would be approximately 260 psi. So for CO2 increase, the increase was 1150 psi, which is about 4.4, almost 4.5 times that of 507. In addition to the high pressure controls that we need in systems, so that'd be your standard high pressure control approach, and relief valves that are used to prevent overpressure For example, in the event of a fire, the equipment is exposed to a fire and you've got a lot of liquid in the system, it can rupture and create some real safety concerns. With CO2, insulation of the liquid receiver. This is not to be confused with what we're doing with HFC systems on refrigeration systems, where we insulate receivers on the roof in order to, what we're trying to do is keep them warm. In this case, with the CO2 system, and it may not make a lot of sense today because we're not talking about transcritical systems yet, but we will cover this a little more in transcritical systems. We would generally insulate the liquid receiver to limit the amount of heat ingress into that receiver. Generally, that receiver tank is going to be held at a saturation temperature of anywhere from 30 to 40 degrees Fahrenheit, maybe a little bit outside that range, but generally those are the types of temperatures that we're holding the tanks at. And over time, the pressure can increase. So by insulating it, this limits the amount of heat that transfers into that vessel. A pressure tank or expansion tank or a fade out vessel is one approach, but generally this is reserved for smaller systems that have a fairly low internal volume. So when the system's exposed to heat, it expands, it has somewhere to go. It just ends up transferring into that storage tank. Now, when you get into large systems with fairly large refrigerant quantities in them, you would need an enormous tank. So it becomes impractical at some point. So another approach, and this is used typically on supermarket systems, in fact, would be a standby refrigeration system. And if you don't have these approaches, then the system needs to be able to withstand the highest ambient temperature that it's going to be exposed to without causing any problem. But you still need to have the relief valves and everything, and the relief valves are there to limit the pressure of the system to the lowest pressure capable component. Okay, this is the way it has to be so that nothing can rupture. But getting back to the standby refrigeration unit, I'll just show you what this means. So you could have your receiver, again, it's insulated. And this is a photo of a cascade system, actually at the Bitzer lab in Germany. So this is the tank here, and you can see on the left we have a heat exchanger. So this would be just a braze plate type heat exchanger. The carbon dioxide vapor is going to expand throughout the tank here as heat is added to it, but it also enters the braze plate heat exchanger up here. And so you could have your pressure transducer determines that the receiver pressure is increased above some pressure such as 450, 500 PSI or so. That would initiate a condensing unit operation here, which would then refrigerate the vapor. Okay, so it's you've got on one side of the heat exchanger, you have basically a refrigeration circuit that cools the vapor side and even recondenses the liquid. And then due to gravity, that liquid just falls right back into the tank. So that's how we can mitigate pressures in a tank like that. CO2 compressors, and we'll probably talk about this just a little bit more when we get into the transcritical side, but CO2 compressors now also have pressure relief valves. Basically, in the event that somebody inadvertently isolates the compressor, we want to have pressure relief protection there. So as always, relief valves are sized in accordance with ASHRAE standard 15. So the relief valves that are on the system, okay, we have to remember those relief valves have to be there. Never assume that when you see a relief valve on a compressor that you can use this in lieu of the system pressure relief. The valve is sized to prevent the casting from overpressure in the event that it's been isolated inadvertently. Okay. Another thing to consider with CO2 is its very low temperature when exposed to low pressures. It has a very rapid evaporation at 1 atmosphere with very intense cooling effect. And generally, steels and things like that have a fairly high pressure capability, which is a reason why stainless steel is used on the high side of CO2 systems that operate transcritically. But copper has a very good lower temperature limit. what we have to be careful with is, when charging systems and that certainly you can form dry ice, which we never want to do. You always want to charge up the system to some static pressure using vapor. So for example, 10 bar or approximately 145, 150 PSI. And if you think about the triple point 75 PSI, so we're pretty much doubling that pressure to make sure we're well above the triple point before we start charging any liquid into the receiver of that system. So you'd put a static charge in basically. And the manufacturer's operating instructions will include this. So for example, with the compressor operating manuals here, it will actually give you some suggested system charging practices to help us charge systems safely. If you were to expose liquid refrigerant to a system that is under a vacuum, you're really going to run into a problem quick, because you're going to start charging liquid into a vacuum, which will result in the immediate formation of dry ice. And at that point, everything is just going to lock up. And at this point in time, of course, you would never want to take a positive source of heat and warm that up and try and thaw that out. You're just going to end up getting into trouble. So cylinders themselves are generally charged with liquid with some vapor at the top. So if you consider a 68 degree Fahrenheit ambient temperature, we'd have a pressure of 830 PSI. We always want to use a pressure regulator, just as we would on gas tanks. For example, nitrogen that we use in systems. You always want to use a pressure reducing regulator to limit the flow and the pressure entering the system and your hoses and what have you. We want to make sure that the gauges are appropriate for use with CO2 as well, so that they have diaphragms that are sealed against liquid, so you don't have gauges that trap liquid and things like that. But there's gauges that are specific to CO2, and of course you just want to make sure that you use those. And of course, we want to make sure that we use flexible charging lines. For sure, it's kind of like in the 410 days, you wouldn't take your existing hoses, or shouldn't take your existing hoses and gauges and just apply them. You always want to make sure that your hoses and gauges and tools and everything that you use are rated for the pressures that they can be exposed to in the refrigeration air conditioning system. And of course, with cylinders, like any refrigerants, you never want to exceed an ambient temperature of 125 degrees Fahrenheit. So just as we'll call it a starting point or suggestion, I guess, if you will, for subcritical type applications, minimum working pressure, if you go for hoses that are 800 PSI working and 4000 PSI burst, and then on the transcritical side, minimum 3000 PSI working and 12,000 PSI burst, then you've got a set of safe hoses. And of course, if you're going with transcritical hoses only, which is probably going to be the case if you're working on booster systems where the high side runs for a few months of the year in transcritical mode above that critical point, you want to make sure that you're using the proper hoses. So so that concludes today's presentation, and I'm sorry if I whipped through that pretty quickly. Anyone who knows me knows that I always put too much in there. So
too much is always good.
But it's before 1 o'clock. This is the good news. Yeah.
Thank you so much, Phil. That was excellent. And, if you did miss something, it will be on the HRI YouTube. Admittedly, I did not record the first 10 seconds of this video, but we got it from the second slide in, so we're good to go. Do you have time to take a couple questions?
Sure.
Okay. This was for Pushpinner. We recently launched CO2-based air-to-water ATW heat pump system in Canada to generate hot water. My two questions are, where can we send our technicians for some training on safe handling of CO2-based systems? Any specific training center in Toronto?
Yeah, well, so as a compressor manufacturer and other compressor manufacturers, we offer training for customers. When it comes to CO2 systems, I highly recommend attending the manufacturer training. Although if I understood the question right, this would be a manufacturer.
Yes. Yeah.
Okay,
Yeah.
that's designing the equipment. So, attending things like this, there's generally CO2 sessions that are taking place in the industry on a fairly regular basis. In this particular case, learning about CO2 used in that application would be really good to learn about the transcritical side of systems. So if you attend the session on February 16th, we'll be talking more about transcritical refrigeration. So for example, transcritical could apply to a regular refrigeration system, air conditioning, heat pumps, the whole bit. So there'll be some information there that you could pick up as well. And we'll be focusing on high side control. How do you control the high side?
Fantastic.
Sure.
We've got 10 minutes. If you have a question, you can open up on the bottom. You can see the chat window. You can put them there or into our Q&A. Let's just take this one from Dave. If there's no temperature or pressure relationship above the critical point, how is the design pressure of the system established?
So the design pressure and we will talk about this again in the transcritical side, but because to answer Dave's question, because there's no relationship between pressure and temperature, we need to find another way of determining what the pressure should be. So the pressure is determined by, what we're looking for is the optimum pressure that would exist for a given ambient temperature and a given gas cooler temperature difference to get us the most efficiency that we can. And I hope that makes sense. It'll make more on the transcritical side when we kind of go through an exercise on the pressure enthalpy diagram. But it will be the ambient temperature, which results in a certain gas cooler outlet temperature. That information generally goes into an algorithm. For example, a control board that controls a high pressure valve, and then it will adjust the position to get you that pressure. So that's how you would do it. And generally, when you select the compressor, you would select it oftentimes you select it in auto mode. Auto high pressure mode is what that means. So when you set it for auto high pressure mode, the software will calculate that pressure for you for a given gas cooler outlet temperature. So let's say you have a 90-degree ambient temperature. Your gas cooler outlet may be 95 degrees Fahrenheit or so. So then your high side pressure valve, it would be determined by the algorithm in the controller that the pressure should be set for, say, 1,250 PSI or so.
Thank you very much. And thank you, Dave. Back to Bushpinder. Why exactly is high delta T required for optimum COP efficiency in a CO2-based refrigeration system?
High temperature difference? Generally, we're working
high
with
delta T. Yeah, water outlet, water inlet.
I'm not aware of the need to have high temperature differences. CO2 is actually pretty good in a sense that when you're pulling, if you're, for example, on the high side, if you're heating water, because we're sensibly cooling the supercritical fluid, the refrigerant starts out at a fairly high temperature. And just to pick a number, maybe it could be 170 degrees Fahrenheit or something like that. And it would gradually cool as it moves towards the end of the heat exchanger. And you're rejecting heat into some fluid loop, whether it's just water for heating or what have you. But like any heat exchanger, you have to have enough temperature difference in order to get the job done. But during the presentation, I mentioned that generally with CO2, you can often get away with lower temperature difference due to its higher thermal conductivity and high heat transfer rates that we can see in heat exchangers.
Thank you very much. And I hope I conveyed that question correctly. Abdel has a question. CO2 cylinders are either liquid or vapor. Is that correct?
You can get cylinders that are going to be vapor, from what I understand. Generally, you're going to buy cylinders that have liquid in them. And of course, there's always vapor in them because the manufacturer would never fill it to 100% liquid. So to generally be liquid in them for the most part. Okay, so you have liquid in there. Otherwise, you would need many, many, many cylinders just to charge a system with a small internal volume of just a a few cubic feet, you would need, hundreds, maybe even thousands of cylinders. So generally they'd be charged, you'd use liquid, and that's why you need to use gauges that are properly sealed. When charging a system, for example, a large booster type system, you would generally charge vapor into the system first until you get up to the significantly above the triple point. So in the presentation, I mentioned approximately 150 psi or so. And then when it's known we're way above that triple point, then we can start adding liquid into, not into the suction of the compressors, of course, but into the receiver. And because you have so much pressure in the tank and you're going to use a regulator, you should have no problem getting liquid into the receiver.
Thank you so much, Phil. And thank you so much for everyone who submitted questions, and the 90 participants on this webinar. That's a good record. Thank you so much. Hope you got something out of the presentation. It is part 1 of 3, so please stay tuned for the other 2 parts. I believe you had the dates posted up there. January
20th, I believe, was 20th. That's the subcritical, and then February 16th will be the transcritical. It'll be at the same time, noon until 1 p.m.
Fantastic. And your email address is there if people have any follow-up questions.
Yep, please do.
All right. Well, until next time, Phil, thank you again so much, and we'll see you all soon.
Great. Thank you very much.